Okay, let's start our second part. With the schedule, my last part of teaching will be on neural network, RNN, recurrent neural network, LSTM, and something like attention-based. That will be very much engineering like focused, and will be probably very somehow difficult for some of you to understand. But I think we have a more like musician background, and people are just maybe more interested in this application of machine learning in music. I think for this second section, I want to introduce you with some, this called Google Magenta. It's specifically for people who are interested in making music using machine learning. So this is so they have a lot of studio. You can click get started. And yeah, if you are a musician, you want to try Magenta Studio. And they have a lot of like neural synthesizers. So they do both symbolic and audio, research and applications. And they also have a lot of web application that you can use directly. So they have the interface where you can play and just see like how to play with it, and you can read blog. So they write this introduction thing for you to understand what's going on, and you can also see code. If you are a programmer, see the source code will be helpful. So a lot of things here. Actually, if you have time, if you are interested, I mean, you can explore on this website. Something I'm really interested in, really fun. Yeah, to play with and also do some art and like drawing, something. Yeah, some music, about music, about art, and something like that. Okay. So demos, blog, whatsoever. So I think our workshop is more like academic focused, research focused, because we are academic people. We do research. For those applications, I mean, it's different focus. Okay, for industrial people, I mean, everything takes a lot of work and efforts, I have to say. But we have different focus. For us, like research, maybe like more like academic oriented. That's what I offer here. But I think for those things, this is a really good resource for musicians to experiment with AI, to create things with AI. And they also use this Google Clive. It's the same as this Jupyter notebook. It's the same layout. It's also a like website interactive coding environment. So it will be really helpful actually for you to learn Jupyter notebook, like, in this workshop, so that you have a better understanding of what's going on in their Google Colab, this notebook. Okay. Yeah, I'll find the notebook when I can. So for Magenta, so here are two blogs that's related to our workshop I want to introduce to you. The first is this called music transcription. So yeah, you definitely know what is music transcription, right? It's from audio to symbolic. Because Sergey just mentioned in the chat that he found this database is in MP3 but not MIDI. Well, the best way, of course, is to have the raw file, right, instead of processed file. Because if you process something from audio to MIDI, there's always some information loss. But if you have to do that, or if you want to do that, this is an application you can use for transcription. I think this transcription is based on the piano. Okay, and so they trained the network. No, the data set they use is the piano data set, the same piano data set that as I used. Yeah. So this is the wave to MIDI to wave. So they transform the audio file of the piano, recording to this MIDI format, which we use a lot in this workshop, right? In this MIDI format. You're not going to listen to this. But yeah, this is the competition, piano competition dataset, and which is not accessible anymore. I don't know why. Yeah. And
No,
I think
it's
they took this
accessible.
down for some reason, and you cannot open this now. But the application is here. Okay, so the trained neural network is here. It's just you lost the original dataset. Right? So you cannot reach this site anymore. So they also use neural network. So it's called onsets and frames, and you can read their paper if you are interested in what kind of structure they used. Yeah, in training this transcription, from audio to MIDI transcription. It's not muted. It's muted.
Can you
You
hear what they
cannot hear
say?
me?
Can you hear what they say? So you don't hear what they say, no? Yeah, we can hear you, but you cannot hear us. Huh?
Oh, I see. Oh, okay. So what did you say? Sorry. Yeah.
Yeah, because there were a couple people who tried to say something, but you were
Oh,
talking.
I didn't listen. I didn't hear. Sorry. Yeah. I
Okay.
mean, you can
No, we
continue.
actually, I think we found that database. It's in actually on in our chat and Telegram. I think there is a link to MIDI. Yeah.
Oh, okay. Oh, I didn't check the Telegram thing, and I think maybe my computer is somehow muted.
Unfortunately, no. So the original link piano-e-competition.com is unavailable anymore. So what we found this website Magenta that it's already processed database. So I believe there's
Okay.
no MIDI files original.
No, there are MIDI files. I just downloaded
It
them
is
from
okay.
this link I just posted. So there is like they have a zip file of 80 megabytes, and it's MIDI files.
Okay, cool.
And they have some gigabytes of audio, which same, I think. Same performance.
Which site, Magenta or modart.com?
This Magenta, the last link.
Okay. Cool. Thanks.
Yeah, maybe they put it somewhere. Yeah, but it's not on this original website host anymore. So yeah, probably you can also still access this this dataset from there, because they of course downloaded this dataset beforehand. Yeah, before it's taken down. Okay, but in whatever situation, let me see. Oh, I see. Yeah, so they kept a copy of this dataset, but it's not original in this original on this original website. I see. So yes, if you'd like to, you can process this by yourself, for sure. But in whatever case, the transcription is still useful for you. I mean, maybe you have other types of file that you want to transform that into MIDI format, symbolic things, then you can use their application to do so. Okay, so expressive time. Okay, this is another thing. Sorry, I'm doing something. Did I close that? Okay, I'm talking about transcription, right? Okay, so this is structure. They have the waveform, transform this to spectrogram, and encode this, and using this encoder decoder, and they get this MIDI-like output tokens. Okay. So they use this on-site and frame kind of architecture, which is use this deep U convolutional neural network. Okay, so this work was done like in 2017, already like many years ago, but it's still available. So maybe we can listen to this. It's kind of like let me see. original. Okay, so this is a transcript encoded in MIDI format. Okay, so it seems they can transcribe multiple instruments here, not only piano, but also kind of string music, string. What is this? So this is a transcribed version. Okay, so you can see how the technique kind of developed, and they can transcribe even, you know, an audio containing different instruments, right? And they can encode this to different instrumental parts, yeah, something like that. But I would say they always choose the best example, because if you, because I tried their application, I run their application, like, you know, in their website. But the generated result is okay, was okay, but not as good as these kind of selected ones. Okay, so what you are listening to is actually what they select as the most thing, the best thing, and the mostly, you know, they will do some engineering work also, like kind of, you know, increase the gain and also do some processing of that. So this is somehow beautified version of their application. But actually, their real application, if you run it, it also works. You know, it sounds they are like you know, lying to you, but it's just not as good as the examples they showed here. Okay, so if you have any types of audio, I think probably you can just do this thing, and which means it bridges the audio and the symbolic theme. Yeah, and I mean, the reason why they do this, because symbolic music is always, you know, you have this mid-level representation, which reduces many data. Okay, much data if you train neural network or if you do processing, etc. So this transcription is something that can bridge audio with the, you know, the symbolic MIDI files. And another thing is this performance RNN. Okay, so here I use the same dataset as what they use. Yeah, this performed piano, competition corpus, and they also they use an LSTM based recurrent neural network. Okay, this is also what I will talk about today about RNN, LSTM, the structure of those neural networks, and okay, so this is one example generated by their model. Let's listen to this. this is just generally speaking too good. Okay. But they chose this theme, which means they kind of can generate something maybe a little bit not better that like this, not good as this, but still, you know, if you hear that, it still have a structure, have some, you know, noise textures happening, and the music is there. Okay. So they kind of also talk about expressive timing, like what we just did, right? Expressive timing and dynamics, which including the micro timing. So this is what they say is quantized chopping, like this. And this is performed by human. Okay. So similar as the example we showed, right? There is kind of the difference, expressivity, microtiming, and etc. things going on in this performance, which is not, you know, encoded in the computer generated, playing. And the data set, is the same as what I used for this, which contains MIDI captures of 1,400 performances by skilled pianists. Here, they notated the note timings, right? They are based on human performance, but not a score, which means it's not quantized. And velocities are also dynamic. So all the pieces were composed or performed on a single instrument piano. Also important, all of the pieces were repertoire selections from a classical piano competition, right? It means, there is certain statistical constraints and coherence in the data set. So, so at that time, the technology was not that developed. So people were still constrained by one instrument. But later on, like what we just showed, right, in this transcription thing, no, this one, in this transcription thing, they can kind of deal with, multiple instruments at the same time. So as you know, the field of neural network and AI just develops so quick that people are just coming with new models, new ideas every day. Like so many people, so many resources were inputted right, in this industry. So it uses 128 note on, and of course 128 note off, and the time shift, right? So they actually use 100 time shift. You can see increments of 10 milliseconds up to 1 second. I believe they use the linear scale, which is not what I showed here. So this scale is what I actually devised by myself. I think it's better reflects, but I mean, what can I say? Like it's like, so this a good processing definitely helps the computer to train. But if you have a real powerful GPU, if you have a lot of resource and human labor to input in that, even if your processing is not that good, but because you have large enough data sets, you have good enough computer systems, you can still generate something really good. Okay. So this is also why like most machine learning thing is happening in this industry, right? That doesn't happen in this academic, because you need to put in put money, resource, human labor into that, and we don't have that kind of resource. Therefore, if you really want to train some application, something like people can use, you definitely refer to this in the industrial resources. For academic research based, you can only bring up some new ideas or work or may not work, but in terms of doing something like this in this scale is impossible. So whatever. but they put in so much resource and they get really good results in terms of training. So this is how they process the data set. So this is much easier than what I did. But the trade-off is that they have a lot more, you know, money and resource to do this thing. And they also did these velocity events. So they categorize this to 32 events, still in linear scale, so 32 bins. Okay. And they just encode them into this one hot vector, right? So on and so forth. Let's see what is this. It's pre-processing. Yeah, so they also did this data augmentation, right? Some time stretching. So this is also what I did when I trained this neural network. Okay. So for the score, I use this key translation, right, to move the nodes up and down. So here they didn't do the key translation. They only did time stretching, which, you know, you a little bit. So it changed the BPM. So increase the BPM a little bit or decrease this a little bit. It doesn't really affect the performance. That's what's their this is their assumption. Okay, so they say, okay, I make each performance up to 5% faster or slower, doesn't matter. Then they do this time stretching, and they get for every one file, maybe you can get 100, you know, similar file by doing this time stretching, which is a commonly used scale of doing data augmentation, right? Oh, okay, sorry, I didn't see this. So they also did, yeah, key transposition. So raising or lower the pitch. So yeah, it is both. Yeah. So they did both things, and they get more files, more data, and to train their big neural network. So they also split each performance into 30-second segments. Because of the kind of limited memory, okay, of the recurrent neural network, but it's also like, you know, kind of doable, kind of yeah, okay, like length of performance. So more examples. Let's listen to some examples. It generates, okay. It's one of the better ones from performance RNN. So they also said that, right, the first one we just listened to is it's not the average performance, it's the better ones. So here are maybe some more ordinary examples. Let's listen to this. So yeah, there is a little bit inconsistency. I would say it is good in general. How do you feel about their model and their results? Okay, another one. Okay, so so they actually put the code of this neural network here. they have this open source repository. And this is the introduction. And they trained this on different types of, data processing, like start a node as page, whatever. Okay, so how to use this. So there are different versions of this performance with dynamic and without dynamic, pitch conditions, multi-conditions, and whatever. So they use they have different versions of training of this same data set. Okay, and if you install this thing on GitHub, download this to your local server, and then you can generate a performance using this kind of instruction. Well, I never installed their application, honestly speaking. Yeah, I'm not a really kind of hard programmer. But if you are interested in this kind of process, I think Tourniquet will be a really good resource for you to refer to. So he does this a lot. Like, he's a very active GitHub user, and doing GitHub things, and also he knows how to install these kind of packages, and for other this kind of industrial or other people's applications. Download this and read the code and how to figure out these settings. For me, I personally don't like it. I like to do things myself because I kind of don't really believe other people in terms of doing things. Yeah, it's everything here is like what they did. It's not what I did, right? So. But it depends. If you like, if you feel, yeah, this result is really good, I just use it. But if you just do DIY, hand make something, it's never like this good, as what they did industrially. So if you are only searching for some musical application you can use, I think this is a good resource for you to refer to. Okay.
So are you basically saying that this is an example of what you were doing, but made like industrially, or you did something similar, but you're making your own activation function and everything, right?
Yes, because we are using the same data set, but the foundation data set, because you have the same data set, then basically you will generate similar kind of things, right? But I'm using different my own ways of data processing, and my own ways of the neural network designing. But my result is not as good as theirs because it's difficult to train a neural network, and I didn't really finish the final round of training of this model because there's something to debug. But yes, generally I just DIY something and I just show you how the process of how you do this. And if you want to try things out yourself instead of using pre-built model, I just show you the principles and the details of doing things. That would be somehow difficult, but I think it's good knowledge to know, even if you don't do these things by yourself. But if you have this knowledge, you know what's going on in their models. It's also a very good kind of knowledge base, right? Okay, so if there's no more questions, I don't know, maybe we can continue to the final part of recurrent neural network, the latent structure, internal structure of neural network. So for neural network, how to build a neural network? There are 3 ways. Okay. The first 3 ways from easy to the most difficult, right? The easiest way is you use the built-in libraries. So if you use PyTorch, they are always built-in libraries like RNN. If you just search RNN PyTorch, you can see, yeah, they have this RNN thing. And this is the same formula like I showed you, right? And they will show you, so they have different parameters. What they do is that they wrote the function for you. So the function is here. So normally, if I do it, I will write it myself. But if you don't know how to write it, or you don't want to write it your own, so they wrote it for you. You just need to call this function. How to call it? So you basically use this comment. So we can try it out. I have this here. It's a very kind of easy thing. You just import NumPy and import Torch. Okay, if you install PyTorch, and for there, RNN, right? I'm using exactly the same comment here as what they do. And because it's a function you are calling, and then you have these different types of parameters, right? And the output, they also give you like what you input, what you output. Everything is specified by this library. And here you can see, so I'm telling this PyTorch, okay, build an RNN, recurrent neural network for me with input size 10, right? With hidden size 20, with number of layers is 2. So the input size, if I go back to, yeah, maybe here, yeah. So for RNN, this is the input. So input size is 10 means this vector is of length 10. Okay, this is of length 10. The hidden layer is A. Okay, so the hidden size is 20 means the vector, the A vector is of length 20. And the layer is 2. Actually, here we only have 1 layer. Okay, so this is 1 layer of recurrent neural network. If you have 2 layers, you have the same kind of thing built for another layer. Okay, so actually you can increase the layers of RNN, which make it the deep neural network. Okay, but yeah, that requires a little bit like not really difficult. Let me show you. Okay, so you just do this same thing. You just make a copy of this like this, right? And this is first layer, the second layer, and what you input to this layer is you input this AT, okay, into this layer. This A into this layer. So this A will become your input, and for this layer, it will have its own kind of memory or hidden vector. We call it B probably, and then it's B0, B1, B2, something like that. Okay, and then from this second layer, I will output my Y. Okay, Y is my output. This Y hat here 1, and then which means I don't output. I don't get my output from this 1 layer. So I'm adding another layer, right? Make it a little bit deeper, and I'm getting my output after these 2 layers of processing. So this will be a more complicated structure. I mean, RNN is already very complicated. Why? Because if you look into this formula, it seems easy. And when you look into this structure, it's also okay. I mean, right? It's unfold this, it's just a chain, and it's just the same parameters, same structure, repeating again and again. So the difficulty comes in terms of training, right? Because you need to train the neural network. It's not like I built it and then it runs, right? You need to train it. So the training of neural network, we really use backpropagation. Right? So you can see this formula here suddenly becomes very, very complicated, right? And this is only for one cell, It's not even for this long chain. So backpropagation is based on these derivatives. Okay. So this J is your objective function, and you compute the derivatives. So you can compare, right? My forward function is only like 2 functions like this. Looks very easy. But when I do backpropagation, everything becomes suddenly super complicated. So this is why like neural network is not that easy as people think, right? Because of these derivatives and backpropagation, training of and updating of parameters. And for RNN, there is more than that. So what is more? Because it is a chain, right? So then you have to, in order to train this recurrent neural network, you need to use this backpropagation through time. So it's not only one cell. So it's not like from this step I do one. Let me use this. From this thing, I do one backpropagation, just one step to this. Okay. So this gives you only one step. So the problem is that because RNN is a recurrent, right? It's if you unfold this, it has many repetitions. Then it will have a structure like this, which means in this graph, maybe this is my final output, Y here, but my input is here. Okay, so this is my input, X. So my X will go through this neural network for many steps. And then maybe I repeat this cell for 5 times. I finally get my output. Then in order to train this thing, I need to do this backpropagation, right? 5 times, 5 steps until I reach my original input. And then I finish this training, this run of backpropagation through time. So, I mean, you can imagine how the involvement, I mean, it's very much involved process, right? And also because there is parameter sharing, okay? You are sharing this W. So although here it's used WT, T-1, T-2, but actually the parameters are the same. You are using the same parameters again and again and again. And when you do this updates of multiple times, you need to compute this derivative 5 times, and then you add them together. But this level of detail is not something that most people know. The reason is that because they don't do this process by themselves. Okay. I know it because I just tried it, write the functions and do this by hand. And then I understand this complexity and where the complexity comes from. And also, people always say there is this limited memory problem of RNN, right? Because you cannot propagating information over long horizons. Why? It's also a problem of backpropagation. Okay, the training. If you compute the derivatives, you'll know after multiple times, depends on your kind of coefficients, your weight, right? Your weight, this derivative may explode or diminish. So, which means if it diminishes, which means, I mean, maybe you only went back like 3 steps, then no matter how many steps you do, the result is the same. If it explodes, there will be more difficult. Okay, then your number will get extremely large, and basically your neural network just broke. So learning extended sequential dependencies requires propagating gradients over long horizons. So this will, the neural network basis suffers this vanishing, exploding gradients and large memory computational footprint, right? Because you need to store all the information for this long time period, which requires a large memory in your computer, and also takes more time to train like one round or one epoch. So there's always trade-off, and neural network is always it's not an easy thing like people think, but nowadays, because of the building of different libraries, right, like PyTorch, like TensorFlow. So PyTorch and TensorFlow are more for programmers use, and we also have a lot of hosts now, you know, for neural network, like more accessible way of doing neural network, like you know, you have this built-in libraries, right? You just input this different size and initiate this function, then you get an RNN. But you have no view of the internal structure of the RNN, but this gives you an RNN by this default library. And then, okay, and then I divide my input. So here in this test, I say, okay, my input is is a matrix, right, of size 5, 3, 10. And this is the sequence length of 5, batch size 3, and input size is 10, right? And I also initialize my H0, which is my hidden vector, my memory. And this is how I initialize the size, and then I get the output. So if I run this, I know my output shape is of this shape, okay, corresponds to what's specified in this file, okay? If you want to know what the output represents, you need to refer to their documentation and check those parameters carefully, okay? So it tells you, okay, this is a tensor of shape L, D times H out, something like this. So then you just check this document, then you know what's, what the output represents. And if we print the output, it will look like this. Okay, just everything is number. Yeah, so this is like one round of this RNN. So this example is just to show you how, you know, convenient it is to use this built-in library. And also for LSTM, so there are many different structures, neural network structure that's already, you know, standardized in these libraries. For example, this long short-term memory, which we'll also talk about today, has more complicated structures than RNN, but basically it's the kind of similar because it's still a recurrent neural network. Okay, and to call this thing is the same procedure. Okay, you just say, okay, NN neural network dot LSTM, then this library gives you a LSTM neural network, and then you just get the input, initialize the memory, and this another memory, and then you get the output just by, you know, calling the functions. So if you go here, torch.nn, nn is the neural network. Okay, torch is PyTorch. So you can see there are many different layers, structures, convolutional layer, recurrent, transformer also here. Those function. So LSTM. That's LSTM layer. Transformer layer. Okay, so if I mean transformer is really like kind of a hot for the recent years. If you want to build a transformer but you don't know how to do it by hand by yourself, you can just call this function called transformer. Okay, and it specifies different parameters here. And then yeah, this is easy. Just call this function and it gives you this output immediately. Okay, So for all these kind of standard type of neural network, you can find the corresponding structure in this prebuilt library if you want to call them directly. Okay, so those there are pros and cons, right? Advantages and disadvantages for doing this, for using this prebuilt library. So the good thing is, of course, it's convenient. It saves a lot of labor, right? So you don't need to write any functions. You don't need to know the details of the neural network. Just call it and train it and use it. Okay, you only need to set up the parameters, right? Just a few of parameters set up, and then yeah, you can get the result. So the cons, the disadvantage will be very inflexible. Okay, so if you are a researcher, if you are a person of requirement, then this will be extremely like constrained way of doing things. Okay, it's very inflexible because you basically cannot change anything. There's no room for you to change anything. Okay, the only thing you can do is to follow their path, and they give you this library, give you this they write everything for you. They just write the functions for you, whatever, right? So they write the functions for you, and the only thing you do is just to call it. Okay, specify parameters and give some input, and just one click. So very much inconvenient. And kind of change functions or presets, and this has this limited usage. But based on your preference or your kind of like your objective, your goal, like why you are using this. So I would say it's not a bad choice, but only depends on your need. So the second way is to do this automatic differentiation. So this is widely applied in nearly all the neural network platforms. So if I click this, there's a Wikipedia page on this if you want to know what is automatic differentiation. Right. So the function of this is that it actually handles the most complicated thing of the neural network automatically by the computer. So yeah, I kind of recommend this thing because I also use this a lot before, because you only write the forward pass functions. Because we know the forward pass functions are always easy to write, right? And your design of the neural network only lies in the forward pass functions. Okay. So so for example, RNN is of this formula. For LSTM, this kind of formula. These are called the forward pass functions, because when you are designing this neural network, your design, everything is within these forward pass functions. But for backward, it's more like mathematical, or like it's more like a arithmetic computation. Okay, it's pure computation. I mean, your creativity is here. Okay, if you have any creativity, you have any ideas of building your own neural network, it's in this in the forward pass functions. And these forward pass functions are always easy to write. You only need to learn a little bit of programming and things like that. You don't need to know like calculus and derivatives, things like that. So this is something that I would say most like neural network designers will recommend. Right, you only write forward pass functions. It's called automatic differentiation. So the pros, like saves human labor in computing derivatives, because backpropagation is only pure computation. I would say if you are a math person, if you like doing things by hand, I recommend this way. But this is super tedious, and it's math heavy, and more importantly, it's very easy to make mistakes. You need to check it very carefully. Okay, every step. If you make one mistake, then this will be a huge disaster. Okay, and it's difficult to find these problems. And the math here kind of, you know, involves calculus, linear algebra, and all kinds of derivatives, I would say, unless you are educated for this college math, and you do it well, or else you need to make a lot of efforts if you want to do the differentiation by yourself. Well, and it's also flexible in designing customized neural networks. Okay, so if you want to design something by yourself, yeah, this is the best way to design, because you can put your designing into the forward pass functions. And the cons, the disadvantage, well, so this problem that isn't resulted from automatic differentiation, because once your forward pass function is fixed, then your derivative, right, back propagation is already done. It's already there. It's a math, and it's not. It cannot be changed by your own subjective feelings, right? And but the problem is that the derivatives itself, it's not the system is doing this wrong. The system will always right. Okay, it's always right. Because, you know, they program this. It's a built-in function. If they make a mistake, this will be a disaster for billions of people, even billions of dollars. So they won't make this mistake. The problem is that the derivatives itself, okay, it itself has a lot of problems, that the scaling issues and other different types of issues, like we just said, right? In this recurrent neural network, for if you do this back propagation through time, then your derivatives basically suffering different kind of, you know, problems. And people devised different ways of dealing with this, like, you know, clipping or enlarging, or using different optimizers to handle this problem. But you need to test and do a lot of experiment of that. Okay, so because this automatic differentiation basically hides the details of, you know, backpropagation. So if you don't do it by yourself, if you don't understand the process of backpropagation, then this function won't give you any information of this process. Okay, this is a kind of built-in library that hides this detail from you, and everything you get is the final result. So therefore, that being said, which means if you use automatic differentiation, if there are some scaling issues of your derivatives, then it's very difficult for you to spotify. And even if you know, it's very difficult for you to debug, to figure it out, because you use this built-in thing, you don't do it by yourself. And then for the scaling issues, it's very difficult, okay, for you to get into that detail, get into that specific place to change this. And also the designer may lose sight of parameter updating process, and you don't know how the parameters are updated. You don't know how the neural network is trained. And I would say training neural network is not like one-step thing, okay? It's not that easy. Usually people try it 100 times, and the best chance is you try it 100 times and you finally succeed. Sometimes it takes a lot more time and efforts to build the system. Therefore, if something goes wrong, then you don't know where it goes wrong. You don't even know how to analyze it, because, you know, certain details were hidden from you. So the third way, of course, is from scratch, right? So write all functions by yourself, all forward pass and back propagation, everything by hand, like DIY. Well, the prompts are very flexible, right? The designer can build customized neural network and design their own optimizer. So now the widely used optimizer is the adaptive optimizer, okay, ADAM. Which means, to use different functions, you also need to have a basic understanding of what this means and how it works. Okay. So the designer is able to control and adjust everything in the system. Yeah, if you write everything by yourself, of course you can control and adjust everything. It's very flexible, and you know everything. You know all the details. So cons, of course, is it requires lots of human labor and math, and tend to be a choice for expert only. Okay, if you are a neural network expert, this might be the choice. But if not, I somehow, I really recommend the second way. I mean, the first way is not really that ideal from my perspective. Okay, any questions so far? Yeah, I know it's a little bit engineering oriented. Yeah. But I think knowing those things, and even if you don't understand now, but just have a general impression of this thing, it's also very helpful for you to work with neural network in the future. Yeah, if you will, or if you listening other people to talk about neural network, if you want to join the conversation, I mean, knowing these basic kind of concepts, ideas are also very useful. Yeah, for you to have a concept of this thing. Okay, so this is the backpropagation for RNN. So RNN is already the most simple or the simplest recurrent neural network, right? It only has one formula, like one type of nonlinear activation, and this is how you get the output. But this derivative already seems very complicated. Okay, let's skip this first. Then what about LSTM? Okay, LSTM is another type of recurrent neural network, which means it has the similar kind of mechanism as RNN, but it's only in the internal design of the cell is different. Okay, the structure is the same. Once you have the cell, you just use it, again and again and again. And if you unfold this, this will be a chain. So this is exactly the same as RNN, right? The difference is that only that the forward pass functions or the internal designing is more complicated. So if you look into this cell and try to understand this type of structure, it takes a little bit time. Okay, so let me see. This is your input. So now you can see you not only have A, right? You also have a C. So you have two different hidden vectors. And you can see the structure becomes, so they designed three types of gate. They call it forget gate, update gate, and output gate. So why is it happening? Why did they design these gates? Can anyone give me a guess? Yeah. So why they don't use the RNN simple structure why they won't design this type of mechanism here?
To control memory. To forget something.
Yes, exactly, yes. Yes, very good, very good. So the motivation is that, right? Because we talked about the problem of RNN here. First, it cannot, but go back for a long time. It suffers from this vanishing exploding gradients. And it cannot have large memory. So actually, LSTM was designed to address these kind of problems in RNN. Okay, because RNN suffering this problem, then people think, okay, if can I kind of design another types of structure that can solve or alleviate this condition. So the answer is yes. So in the 1990s, a group of people, they designed this LSTM neural structure to kind of tackle the problem they encounter for RNN. So here, how do they control this memory? Okay, so this forget gate, you can see. So when the A comes, so actually I think they use C as their memory, mean memory. And when C goes here, and you compute something, so it's a gate, okay, forget gate, or okay. So the formula is this. So they design this forget gate. So when your memory comes here, you can make a decision like I want to keep this memory or I want to discard this memory. Okay, so it really depends. If you think about yourself, okay, just some generally, when you are like write a piece of music, when you compose something, or when you even talk constantly, right? If you think your speech now is related to something previously, then you say, okay, I want to keep this memory. If you start a new topic or you just change this direction, and for certain things happened before, I want to, I want to have this choice that I can just forget it or just don't care about that, right? So this is the same mechanism. It is when your memory goes here, it makes the decision like I want to keep the memory or I want to discard the memory, and then this computation will give you the chance to make the choice. Okay, but previously in RNN you don't have this mechanism. You cannot just choose to forget or not. You always have the same way of processing your memory. Okay, so this is forget gate, and when I come to here, there is something called update gate. So update gate means anyone want to give a guess, or anyone like somehow if you comprehend this formula here or whatever, just a guess. I mean intuitively. Want to try? Okay, so update gate means update the memory, right? Because now I have a new input. I have my old memory, and now I have one new input, and I'm deciding like how I would update my memory, how I would process my memory. So this is also a choice here. So there are two ways, right? If I have a new input, I think this input affects my current memory, then I will add this input to my memory, right? But sometimes this input is not that important, which means, okay, I have this new input, but my memory basically don't change, which means I can basically skip this new input because this is kind of, not important, to my current conversation, right? So like something that doesn't carry much information, I can just skip it. So this gate, update gate, gives you a choice that I want to change my memory or not. So I can choose to change it, and then I can add these two things together. I get my new memory, and I can also choose to discard or just ignore this input, right? So this is a new mechanism that wasn't presented in RNN. So in RNN, you have no choice. For every input, you have to take it in. Okay, so for every input, you take it in and you use that input to update your current memory. So this is the default way for RNN. But now you have more choice. Okay, you have a choice. You have choice to forget your memory, and you have a choice to not update your memory. And for output gate, yeah, it's just for how do you get your output, why, and yeah, this is output. So output is like it is kind of the similar structure as the RNN. Yeah, you are producing some output, and you are using this update A to produce your output Y. So this is intuitive understanding of LSTM. Okay, and everything I just said now, you can find this corresponding part in these formulas. So this is the new structure. It's more complicated, of course. And if you want to compute this back propagation, that would be a huge suffer for human being, I would say. I never tried this. Okay, I never tried to really compute this. I mean, well, I probably tried once, only once. and it wasn't a successful attempt, really. For RNN, it's still like workable for this type of structure, okay, RNN, because it's easy, but for LSTM, that would be a huge project, at least for me, to do this. Okay, so I think we can talk about this thing. So we talk about backpropagation, right? A lot. Like, but what is backpropagation? How do we use the derivatives to update parameters? And why we can use derivatives to update parameters? These are all questions. Okay, so people will tell you, okay, I train a neural network, I do backpropagation, and I update parameters. But what about the details and the motivations, like why am I doing this, and the theoretical foundation for me to do this? So I want to show this this basic concept, basic structure using this very simple computation graph. Okay. So here, I have three parameters, okay, which is A, B, and C. Three parameters, and A is 5, B is 2, C is 3. Okay, and then I have some very easy computation for them. I compute U is the B times C, right? So what is U, right? It's 2 times 3 is 6. So U is 6, right here. And then after I computed U, and then I compute V. Okay, V is A plus U, A is 5, U is 6, then I have V is 11. And then come here, I have J equals the V square, which is 1 to 1, right? And very easy computation, like. So I think everyone understands this at least, okay? So this is called a forward pass. So I have some initialization of my parameters, and I do this forward pass, forward computation until the end. So this is very easy. So the question now is that I want to update these parameters. I mean, okay. So let me go there like later on. Now let's talk about derivatives first. Okay. So to compute derivatives of functions, like here, what I can do is use dj dv, right? Compute derivative of v. What is this? Anyone know? Anyone tell me what's derivative of this function? No one. Do people really?
2v.
2v.
Yes. Yeah, I'm just wondering if people really learn the calculus or not. Yeah, very good, very good. At least you remember some basic calculus. Yeah, then yeah, I'm such like relieved for yeah. I mean yeah, this is already enough for you to understand a little bit of this calculus. It's not super difficult, okay? Not super complicated. So here to compute this derivative, so I have two inputs, right? A and U. So I will use a partial derivative, partial V, partial A, right? What's the derivative? G1, right? And for U is the same, partial V, partial U is 1. And here, my function like U equals B times C. Again, I'm computing this partial derivative, partial U, partial B. First, what is this? Anyone know the?
1.
No, this is time. Yeah, this is B times C. Multiplication derivative.
C, I think.
Yes. So for multiplication, when you compute the partial derivative of B, it gives you C. Partial derivative of C gives you B. And this is already the end. Okay. So now I computed all the derivatives of my functions. So what's the purpose? What's the meaning? So for derivatives, it means like the change, the rate of change, right? So so for example, in this circumstance, I compute my v equals 11, right? So if I want my v to be 11.2, and then how much I should change a, right? Okay, I don't know if it's too complicated. Okay, not really, maybe not a good idea to do this. I think, but at least you know the derivatives. Okay, so now, I mean, my question is that, okay, the question is I have forward pass and I somehow computed the derivatives, and now I don't know how to use the derivatives. So the idea, the objective is that now my g is equals v squared. What if I want my g to be 0? Okay, so my goal, my objective, my final objective is to make this j equals 0. So in order to make j equals 0, I need to adjust these numbers, right? I need to adjust these numbers to make them their final computation after computing u and v and g. Finally, this j equals 0. But the thing is that it's not that easy, right? It's not like I want the j to be 0 and I can immediately find corresponding ABC to make it such. So this is where the parameter updating comes from. So you are updating these parameters, change them a little bit, right? Step by step, gradually, and finally, maybe after multiple times of iteration, you finally find the the number here, the assignment here that will produce a j, kind of near 0. Okay. So how to do this? The mechanism is called gradient descent. Okay, so this is another Wikipedia about gradient descent, and this is the graph I use. So this is the principle of this. Okay, so this is the initialization of your parameter, and then you do this updation a little bit, okay, just gradually every step. So your goal is to make this x0 to be here. So this is your final goal, but you cannot go from x0 directly to this point, right? And then you have to find a way, like, compromise and somehow doing this, step by step, and then gradually I'm approaching my final objective. And the formula of this gradient descent is given here. So here I use A. A is the parameter. Okay. So every step, the next step of A here, I compute the derivative. Okay. I use the current A minus. So neta is a small number. Is called the step size. Okay. This determines how large your step is. If neta A is large, you just go a long way. If neta is small, you just go a very short. Okay, very short way. So this determines your step size. And this is the derivative. Okay, like j, you compute the partial derivative of j over A, and then you update your current parameter to a new one. And by doing this multiple times, then gradually your parameter will approach this state, and then you finally achieve your goal here, okay, to make j equals 0. So this is how you use the derivative, and this is why we compute derivative, okay, in neural networks in the backpropagation. It's basically to update your parameters and make them fit or approach your final objective here. So here is an easy example. But in our neural network, this recurrent neural network, actually we use this thing called categorical cross entropy loss. Okay. So here either the G or L. L is the loss, and G and they are all this our objective function. It's called objective function, and your goal is always to minimize the objective function. Okay, to make this the lowest, because it's loss, right? You want to make the loss near zero. So this is the formula for cross entropy loss, categorical cross entropy loss. So you have the pi hat. So P is the probability. This is the real probability. This is your computed probability, and you want to make this loss as low as possible. Okay, just to minimize this thing. And how to minimize this is to so for this formula, there will be a different computation graph, but it will be something like this. Okay, just the functions are different. And what you would do to minimize this thing is just to do this step, right? Back propagation back to your original parameters and update them, using gradient descent. Everything clear, or do you have any questions regarding this explanation? If there's anything unclear, I can explain more. Yeah, no problem.
Why is it, if I'm asked, this gradient descent exactly is graphed like this, like concentric circles going into center? I mean, for what reason?
Yes, yes. Because actually they use this thing is kind of for this plane, right? Or plate kind of graph. But usually, when I was in undergraduate, we use this a lot. So this is the lowest position, okay, the lowest energy position. And what you will do is you will just go down gradually, okay, until you finally reach the lowest position. This is the minimization. So here, actually, this is something. It should be in 3D, but they plot this in 2D. In 3D, this should be something like this. Okay. I don't know how to describe this. Yeah, I don't have a real good drawing here. No. But whatever, this is something like this. If you think about 3D, this is something like a ball, okay? And this center is the lowest position of this ball, and everything else is just up, okay? That's why you are going down. You are sliding down until the center. So the center is the lowest position, okay, in this function. Just different visualization of things like I think people use. Yes, yeah, it's something like that, yeah. Anything else? See if there's anything. Okay, so now let me show you the code. Okay, so we talked about these different ways of doing things. I showed you this built-in library, right, in PyTorch already here. So let me show you how to build neural network using the second approach. Okay, using automatic differentiation. So here is what I did for this RNN neural network. There are several steps. The first is parameter initialization. So you need to initialize your parameter. I mean, basically providing this this start point, right? I'm giving this x0 or a0. So this is my initial position. So this is how what I did for this parameter. So I just ran randomly, okay? I use this random function just randomly give them, give a range between -0.5 to 0.5. And you can see everything here is, appended, right? By not appended, but pre-appended by torch. Because I'm building this neural network on this PyTorch platform. And the only thing why am I doing this? Because I want to use this automatic differentiation in PyTorch. Okay, so this is a test of this function, which means, this function just runs and gives me correct size of output. And then I will write my own like forward pass function. Okay, so this softmax doesn't matter, but this is the forward duration. This is the function here. This is this function. Okay, for one step, for one cell. So I will write it. So this function gives me one step of forward computation. So you can see I have this x. So this gives me a, right? This torch.10h, and this is the linear combination, right? Matrix multiplication of this WAX. You can compare this with this. It's exactly the same thing. Okay, exactly the same thing. WAX, X, WAA, A, BA. Right? WAX, X, WAA, A, and BA. And then I will put everything linearly through this 10H activation. And then I get my A. And for Y, it's the same as what I wrote here, right? Softmax of this linear combination of WYA, A plus BY. All right, so here you can see. And this it's actually very simple code. Only 4 lines if you think about, if you also can, think about this kind of, the file like type transformation, but the main part is only 2 lines, just these 2 functions. And this is another forward thing. It's the same, just 2 functions. And I'm testing this, whatever. And this is my loss function, right? We use the cross entropy loss. And this is how I designed the loss function. And then I would write the forward pass, because previously this function is only for one step, right? For one cell, but now I need to concatenate these cells for multiple steps to make it a recurrent neural network. So in this forward pass, okay, I would also use my input. So these are my input data, kind of process that, and I will call this forward. Okay, this function is what I just wrote, forward duration. Okay, I will call this function I just wrote, and I will also I will also design the loss function. Okay, so here this loss function is the cross entropy loss here. Okay, and this is done, and this is everything for my function writing for my forward pass. And for the parameter update, actually I didn't write my own function at all, because I called this thing called loss.backward. So this is the automatic differentiation here. Okay, this is the automatic differentiation function in PyTorch. Let me close this. Okay. Okay, so this is the automatic differentiation in PyTorch. So now I defined my loss, and then I just call backwards. Then it computes this derivative for me, which I don't need to do by hand. And then I just update everything here, right? Use this gradient descent we just talked about here. So using this formula to update all my parameters: WAX, WAA, BA, WY, and BY, things like that. So this is the the code, yeah, of this RNN. Questions? Okay, so I hope these explanations are clear. And after this, I think finally what I want to say is what I did, right? What was the structure I used in this generating this expressive music, because I talk about like how I did the data processing, but I didn't talk about the structure I use. I mean, literally any recurrent neural network structure can apply here. Okay, you can also even design your own structure. You don't even need to use RNN or LSTM. So you can design your own recurrent neural network, which means the structure is basically like this, but you can just, DIY or improvise within this cell. Okay, just do something of your, put your creativity into this cell, and then, design some of your functions. So you can use RNN or LSTM, or the transformer now, like more advanced, like producing better results. So here, what I designed myself is something called LSTM attention. So this is the cell I kind of designed. I mean, you can do it differently, and write your own functions. So why am I designing this structure? So what's the motivation? What's the idea behind this?
Is it a question?
I'm just taking some water and give you some time to stare at this something, yeah, for a while. And yeah, but of course you can answer, like, I mean, you can just tell me your thoughts, like what's the difference of this and whatever.
To have better results.
Well, you have 4 inputs, 4 outputs, no?
Yes, exactly. Yes. The main reason for me to design this, yes, it is because I have multi input and output. It is multi argument. For these standard neural networks, they only have one input, one output. But if you have multiple input outputs, there are certain dynamics you need to consider. So traditionally, when people do this music generation, right? You still have at least, like we said, at least you have pitch and duration, right? At least you have these two inputs. But what the engineers really do is what I showed you, right? If I have 8 categories for duration, 10 for notes, and I just multiply them, right? And I make these 2 inputs as one input. I just enlarge the size of the vector, but I still use one input. So this is one input. This X actually incorporates my pitch and the duration, right? And then I have one input, and I input this here, and then I can use this standard built-in library. But the problem is that, as I said, right, if you have large numbers of inputs and you still do this scaling, then your vector will become incredibly long, and then it's not really instrumental to train your neural network, especially if you don't have enough data set. So, but here, why I don't kind of just use the similar structure? So what I'm thinking about is that, so one easy way, if you just don't think, don't use your brain, is that okay, I have 4 inputs, and I have my memory, and I just, you know, update. I just find these things and just use softmax of them, and then I get 4 different probabilities, and I just sample them. Okay, and then I get my new for output. So there will be a problem actually, which is the interdependency of these arguments. So which means, if you think about this, when you write music, when you compose a music, for example, like for now I have a note of C4, maybe of duration, I mean quarter note probably, and now I'm generating the next note, right? And now I see, okay, first I determined the pitch will be maybe D4. Then what about the duration, right? So when the conditioning, the conditioning here is that my decision on taking D4 actually affect the duration I'm choosing. I don't know if you can understand this. I mean, they are not independent. Okay, it's not okay. I use this information to sample D4 and use the information to sample this duration, maybe 4 or something, like separately. It's like, for example, I know C4 and G4, right? G4. So they are kind of in harmonic in this fifth scale, and I know if I go from C4 to G4, it is safe, and I may want this G4. I can make it longer, right? If you consider this classical music situation, I can make it longer. But let's say I'm going through a scale, okay, of C, D until E. Okay, and then obviously this D4 is a transition note, and usually the transition notes are comparatively shorter than the mean structural note. Right? If you think about this in this conventional way, okay, I'm not saying like in all the situation it has to be like this, but in this conventional way, if I have some, you know, auxiliary note or just not that important structurally inferior note, right? I just make it a transition. I just want to go from C to E, but I'm just adding a small note there to make this connection. And then my choice of this note pitch affect my choice of the duration, right? So the idea is that it's like this, and it also works inversely. For example, I have C4 and 8, and then now I sample duration maybe very long, 16. Then I should be really careful about what the note I'm choosing, right? If I'm choosing something that's inharmonious with C4, like maybe I choose some tritone, then I make these 2 notes, you know, consecutive or even simultaneously for a long time. That will probably be very harsh, right? It's inharmonious. It's unfriendly to your ear. So if I, especially right, if they happen simultaneously, because we are now generating this polyphonic music, many notes happen, you know, simultaneously. If they happen like they sound together and they are like inharmonic, this will be a problem. But what if I use this and I predict some duration, maybe very, very short, like 1. Oh, sorry. Maybe duration like 1. Then this duration is very short. Then I don't care much about if it's inharmonious or not, because it will just, you know, happen, just end very quickly, and will abruptly, like, I will just jump right to the next note. And structurally, the next note is more important, and this note is just some, you know, transitioning, and nobody will even pay attention to this. Then I just don't, I don't have to make it, you know, some specific harmonious note. I can make it maybe C sharp or some tritone or even something, you know, very, very, very weird. Okay, so I don't know if it's a good explanation or not. But the general idea is that I have the input, I have multiple inputs, and when I have multiple outputs, I need to consider this interdependency among, right, these outputs. Because now I'm using a generative system. I'm generating something. So when I use this to generate these four properties, four quantities, so actually I cannot generate them simultaneously. So if I make this like one long vector, then then this problem doesn't exist anymore. The problem is I'm inputting them separately and also generating them separately. Therefore, this interrelationship, interdependency actually matters much in my consideration. Okay. So here I'm saying, okay, I'm generating the node first. And then the node that I sampled, I determined will affect the duration of my choice. And then the pitch and the duration will also affect the velocity, right? And this node, pitch, duration, velocity will also affect the time shift. Okay, so this currently generated thing also affects this. So there is a kind of chain or some sort of relationship, interdependency among these values. So in order to capture this structure, then I designed this kind of neural network. How? So basically for this thing you can see, right? First, I generated xn t plus 1, and then I'm reusing what I generated into the second, right? So I'm adding more argument into the generation. So when I sample xn, and then I input this as my additional information to predict this xd, right? And when I sample xd, I use these two sampled output as additional information so that I can predict this velocity better. And I'm not adding another velocity here because velocity is comparatively not that important information, right? So I can probably I can just ignore this, but you can also just adding this in here. Okay, it's just my choice. I didn't add this here to keep my parameter size a little bit smaller. And then I have additional information and I can predict the time shift here. So this is how I first perspective on dealing with this interdependency. And the second thing is that actually I'm using this ATT called attention model. So attention model, simply speaking, it weights the different arguments because I have too many different arguments here. Like for RNN, you only have 2 arguments, right? And for LSTM, it's always one or 2 arguments. So you don't really need to weight them differently or weight them very. You don't need to like pay too much, do too much of this processing here. But here, because I have 4 inputs, here I have 5, even 6, then how to weight these different inputs is a problem. Is a important problem for me, like to do that. So so for different these kind of inputs, I put different weights on them. Okay. Yeah, I somehow a little bit forget about. Okay, I'll get into the detail of how I computed this attention when we look at the code. Okay, I forget this a little bit. I did this work last year, so some details already gone in my mind. But whatever, I actually computed the attention and to re-weight. Okay, weight all those different arguments so that it can better kind of reflect and do better job in this prediction. And also attention model or the transformer. Okay, if you ever heard about that, transformer also use attention model. Actually, the truth is, once this attention mechanism came in, it kind of, make this RNN LSTM outdated. So nobody now use LSTM and RNN anymore. Once the attention came in, just a few years ago, yeah, there's a paper called "Attention is all you need." Yeah, if you want to, it's a very influential and important paper in this temporal neural network process. It's called "Attention is all you need." Then in this paper, they introduced this attention mechanism, and this kind of revolutionized the field of recurrent neural network. And the attention mechanism, the reweighting of those different reweighting of different arguments based on the current context is something that improves the performance and also makes everything makes more sense. I mean, in this situation, if I don't use attention, I don't even know. I don't even believe this neural network will work. Honestly, it's only after I use attention, I think, okay, this thing might work, logically. So attention is all you need. This is also the foundation for the transformer. Okay, for everything transformer related. So this is the structure of this neural network that I just DIY'd. Okay, I designed. So as I said, you can just do your own thing, design your own functions within this cell, and etc. Okay, so this is the one of this example. Okay, let me do this later on. Let's look into the code first. Okay, so for this specific system structure I designed, so here is this is the function. Okay, this one step forward function. So you can see there's a lot more complicated things happening here. So first I get this for AN, AD, AVAT here, right? Because I have a C. When I input C into this, I need to separate them, right? Into AN, AD, AVAT. There should also be AP, but I didn't, I forgot. Where is it? Okay, so here, this kind of, C tilde, and so this structure actually imitates the LSTM. Okay, LSTM. So you can see this GF is the forget gate, U is the update gate, right? Like this, right? So there, this is the gate FU, and output something like that. So that part imitates the LSTM structure. Okay, this is forget gate, this is update gate. And then to update the C, right, I multiply forget gate. So this is basically this one, okay? The forget gate times the previous memory, the update gate times the update memory. So it is here. Okay, so C previously C tilde, and then I get the new memory. So this part is the LSTM part, and this part is this attention part. So how do I weight this A? Okay, so I concatenated this AN and all those input. This is my input. Torso transpose. Okay, so I think I need to know what is AN. So AN. Well, I really should do better, documentation. So matrix multiplication of an and Vn. And then this is my weight. Okay. So I compute my attention based on this context there. And then use Vn to multiply this En. Then this is my weighted sum, you can see. And then I compute my output, use this softmax. So I think the An should be PVT. Well, it seems yeah, I cannot find this right now. What is An? Yeah, somehow I forgot about this detail of that. But this must be some kind of context matrix, okay? So that I computed this attention basically weighted the input and this An. Oh wait, whatever. I mean, if you are interested in these details, you should look into the paper, okay? Transformer paper and this attention paper. And what I did there is basically the same idea as this attention, okay? I've just lost this track of this particular thing, what the quantity there. Okay. So so talk about this. And yeah, this is my one step forward of the cell. And my forward path, so you can see the structure is the same as RNN, but it's just the function become more complicated, a little bit more complicated. So here, of course, again, I write out my loss function. It's still the categorical cross entropy. And then here I call my one step forward function here, and I compute the loss. And when I update parameter, again, I use the second choice, right? Using this automatic differentiation. So I call this function automatically, and then I don't need to compute the derivatives by myself. And the PyTorch basically handles this computation graph. Okay. Okay, so also En is my parameter. So this is the parameter of this attention neural network. So in attention, there is something called K and something called inquiry. Okay, so here K is the case and A is this maybe I shouldn't improvise now. Okay, so let's just look into this. This also has some Wikipedia. So this is structure. You can see this multi-head attention. Maybe we just read the paper. Okay, so the paper is open source. Anyone can read it. Okay, so it has you can see different values of, these matrices. So this is the parameter, okay, of the attention neural network. It's called Q, or question, key, and value. So QKV. So this is a kind of intuitive name they gave it. So in my in my design it's similar things, but I don't remember why I call it A. But you can see there are three types of matrices, parameter matrices, and this is how you compute this. Okay, Q, K, and V. Basically, you just update the attention, compute the attention every time do this convolution with the current input, so that it provides you a context. Okay, so this is the neural attention network. And in terms of training, here I use this ADAM, adaptive optimizer. But I use this, but I didn't compute this myself, right? I just call the function, the built-in function. And this is where the problems comes from, because I didn't write the back propagation myself. I have no access to check the process. And when I use this, then I actually suffered from some, scaling problems there of derivatives, which makes my neural network doesn't really converge. And yeah, it's somehow like I tried this multiple times. It doesn't really provide something satisfying, honestly. I mean, if I want to debug this, then I need to probably compute this derivative myself, and also redesign this optimizer and make everything scale correctly. And there's making sure this internal flow works, and there's no like vanishing or exploding problem of certain gradients. Okay. So this is very, very tedious and cumbersome work to do. And I didn't do that, honestly. I just shift my research direction somewhere else. But this is the second option of building neural networks. And I also suffered the cons, right? The disadvantage, which is I lost sight of the parameter updating, and some problem occurred, and I couldn't find why this is the case. So for this from scratch, I also have an example, which is also I did. So I didn't continue with this program for a certain reason, and I just changed my direction to something called Helmholtz machine. It's difficult to explain. So the basic structure looks like this. So it's a predecessor of this VAE, okay, variation autoencoder. And I choose this model for certain reason, and because it's more theoretical, and it's comparatively simpler, but you can do more foundational research on this, whatever. Okay, and I can write all those basic functions. This model was brought up in 1995. Okay, so very, very old thing. And people somehow didn't continue with that for a certain reason. And I picked it up for a certain reason. So it actually use this variational free energy as this objective function, right? So in most neural network in this current kind of industrial, they use this cross entropy a lot, right? For categorical, and also use square errors like that. But here it use variational free energy. But of course, VAE, variational autoencoder, also use this kind of variational free energy. It's just a variational method of training neural networks. So what I really want to show is here. Yeah. So here, actually, in this prototype, I did this back propagation myself by hand. Okay, so you can see these are the formulas. And I mean, the forward is very easy. The forward is something look like this. But if you want to compute the derivatives, you will basically do something like this, okay? Just compute the derivative. I mean, I would say this is comparatively the easiest derivative already. I mean, this is already the easiest thing. Yeah, if you have more complicated structure, the process of derivative will be more complicated. Okay, and here I also use this outer product, inner product, arithmetically demanding. Okay, but so if you look into the code, so this is part is these derivatives. So usually, if you call this thing, okay, loss dot backward, which is automatic differentiation, right? You only do this. So this gives you a hidden part of this function. Okay, so if you write that out, this will be something like this. So they compute this derivative, but they hide these functions for you, and you just call one function. But this is the detail of derivative. If you want to write derivatives by yourself, these are the functions you will do. So you can see there are not many lines there, right? It looks okay, looks simple. Yeah, it's only, but actually not. Actually, yeah, if you really want to know how to compute this, if you really want to learn how to write this code, I mean, yeah, you need to learn some math, learn some arithmetic things. But whatever, this is what I want to show. If you want to do things from scratch, also write out your own backward function. This is what you will do. Okay, this is the derivatives I compute, and this is how I just update the parameters here, right? The u is my parameter, and I updated this for one step. Okay. Okay. So finally, let's listen to this generated example. As I said, because my neural network doesn't really converge, so this example might sound not that good. Yeah, but I'll play this. Well, how do you think about this? I would say this is some generation of totally not well-trained neural network, because the loss was very high, not nearly like half trained. So I can imagine if I really train it well, if I can find a way to make the neural network converge, I think it will generate really good music. I mean, for now, some notes may sound, abrupt, and the dynamic also sometimes change too much, and also the pedal is on all the time, and some inharmonious random notes are happening. there. Okay, yes, but at least I think the expressivity is really there. Yeah, at least the success is that we achieved expressivity. Although some, harmony, some chords are not really well coordinated, and also the inherent or some latent structure was not captured by this neural network. But at least I have this expressivity. I think this sounds more expressive than the Google Magenta one I just showed you, right? This industrial piano RNN, which is partly because because of my data processing. Okay, I think it's because of my data processing, because of I use this scale, this male scale of data processing. So I have finer duration or time shift. I have finer of this micro timing captured in my scale, but in their model, right? In their model, they use everything just linear scale. They are engineers, okay? So they do everything as simple as possible. So they use this linear scale, and yeah, and then their music, although it's well trained, but they cannot capture this micro timing, okay? Because the smallest unit they use is like 10 milliseconds. 10 milliseconds is not enough for expressivity, okay? It's not enough for expressivity for this micro timing performance. So I think at least I succeed in some aspect, at least in data processing, but the training is just, maybe I just designed some neural network too complicated. That's the system, right, cannot handle such complicated neural network, so it just stopped working. Just say, okay, I'm not training. So yeah, it's just some halfway kind of thing. If I have time, or if I have any chance, I will continue with that. If I get if I just ever get better result, I will probably even publish this. But for now, let's just do something else. So this is the file of generating something like what I just did. Okay, this is the generation, expressive piano performance generation. Okay, use MIDI format, and also yeah, incorporated some writing into this notebook. And this is the data processing, the neural network structure. And this is something ready to use, okay? I will also share it. I will also like upload this to the GitHub so that you can have access to this and you can experiment with this. So in this thing, okay. So actually I put all my functions into a utils file here. Okay, this utils. So yeah, everything of my functions are here. So if you want to check in the code, check in the details of these functions, you can just open this thing and look into this file. But here I'm just hiding the information and run this. Okay, so just load some default values, and this is the how do you initialize this generation. Okay, so you can initial with one node, right? This is the one node. You can just provide just one random node to this system, and then it will just generate the whole corpus for you. Or another way is that you can condition it with some melody. So actually, I preloaded some processed melody of piano performance into this. And you can also condition your generation on a piece of, okay, it's not one random node, but a piece of music, and then the system will generate this continuation. Okay, so then here you can choose either random node or melody. Okay, so if I choose random node and I just use input, so this is the random node the system generated for you. For me, this is of 103. Okay, this is the note value, the MIDI number. This should be the the duration, okay, in milliseconds. So my duration is 46 milliseconds, and this is the velocity. So my velocity is 103, and the next one is the time shift is 0 because this is my first node, so it's 0. And so steam pedal on or off, I see, okay, this is off. So there's no pedal in the beginning, at least for this node. And then I can choose like in random initialization or just some random initialization. Okay, let's see random initialization and just run this. And temperature, I mean, you can change this to some other number. But in this circumstance, it won't work because my neural network doesn't converge. I mean, but you can also try. It doesn't matter. You can just change it to anything you like. And this is durations. And I see, okay, generates 1,000 nodes for me. And then just run generate sequence, and then it's just generate. Okay, this is my generation. You can see there are 1,001 nodes. And then I can write this to MIDI file. So it's on my desktop. It's called generated LSTM. Okay. Then I can check my desktop. Okay, there's something called generated LSTM, right? Then I will import this into my Audacity. Okay, this one. Okay, so you can view, this is the generation. Okay, varied dynamics, things like that. And yeah, the bad thing is that because my neural network just, you know, is not well trained, so the pedal is always on. Yeah, if I train it better, if it converts, this will be much better condition here. But whatever, let's just play it and listen to this. Well, it's good. It's very unexpected. Honestly, I didn't think. Yeah, I didn't expect this will be this good. Honestly, yeah, I thought it somehow sucks. I mean, at least, I mean, if you read this training result, it's really like really bad. It doesn't converge at all. It seems it doesn't train at all. I mean, the loss is just the same, even increase. So
but what's once again the reason it doesn't converge? So you didn't have enough time? You didn't spend enough time for this, or what's the reason?
the reason is the derivative. Yeah, there, as I said here, right, there will be some derivative, maybe have some scaling issues, and because maybe my neural network just too complicated, and mostly because I have too many parameters. That's a problem. I have too many parameters here, right? And this impossible. Like if you don't scale it this well, I mean, if you have 100 parameters, then it's and you have the same kind of, you know, step size, then some parameter will update very, very quick, and some parameters don't update at all. And then your path here will probably be like this, okay? And then it just don't converge. It somehow like goes there, but it can never goes there. It always diverted, you know, because there is no balance between your updating of parameters. Because something, if one parameter updates really quick here, and it already reaches for all your other parameters, it will impede the updation of your other parameters. So for example, this thing starts here, but it's updates slower, and then after this parameter stopped updating, and then this one will also stop updating somehow, like very, very slow, and it will never reach the lowest point, which makes, you know, your loss cannot go there. So yeah, and I mean, I tried. I honestly tried, because at first I used this. I didn't use any optimizer, just some gradient descent, very, very classical way. Later on, I tried with this ADAM, adaptive optimizer, and because people say this will give you better results, it will scale these parameters for you. But I tried it; it didn't really do the work that I expect. And so I think the best way is just me, you know, just sit down and do this derivative by myself, and then I can find out which parameter was problematic, and I just go there and just adjust that, or else if I find this structure doesn't work, right? This system something is, you know, the kind of this going against each other, I will probably change some function here that makes them more compatible with each other, so that the parameters can, you know, just yeah. So whatever, yeah, this is another topic. I cannot say anything definite until I find the problem or I solve this. But yeah, okay, what else? What else? Okay, so I said, right, here, so in this generation, I use this random note generation. Okay, I think this is good one. Let me save this thing. And I also said, right, we can choose melody. So we can condition this thing on melody. If I choose melody here, okay, and you can choose how long you want this melody to be. I mean, I can choose this longer so that you know what this melody is like. But this, okay, I mean, well, we can try and you understand what I mean. But whatever, like, let's say like I have a melody, then my input is this, okay? This is 100. 100 notes, okay, from my preconditioned melody. And this init type should be 0 init, okay? Because this is the, I mean, oh, it doesn't matter. It doesn't matter. It will compute the init based on this melody, because I'm conditioning on this. So yeah, maybe I just should do this. And okay, run everything, still generate 1000 notes. And now my generation is more. Okay, it should be 1100, right? Because I have 100 nodes as preconditioning, and I'm generating the later 1000. And let me write to MIDI file. And then, okay, let me import this into my Ableton Live. Okay. Okay, so you can see the graph doesn't change very much. Let me just play this. Right? So for the first several seconds, you can hear, right? This is the melody I used. So this is a well composed piano by famous composers. So you can hear this very well structured thing. And after that, and the computer started to compose. Maybe I stop here. So the idea is that if I train it well, right, it will basically imitate the style of this melody and maybe just repeat this motive somehow, right? Continue with this motive with good continuation, which means, okay, I can just I can input a piece of music that probably I wrote and to the system, and this system can generate some good continuation for me, right, to complete my composition. The thing here is that after I input this 100 notes, the system doesn't really continue with that. It doesn't recognize the structure, right, in this previous composition. It just starts somewhere like randomly and starts its own composition. So this is a sign of showing that this neural network is not well trained, right? It's not well trained. I mean, I'm saying, so my expectation is that if it's well trained, it should be able to capture the general structure of the music so that it can at least repeat or recognize the motive I give it to it, and then it can develop on this motive and continue with this motive, but not suddenly or abruptly to change the direction or the composition. So I think for this thing now, for my current trained parameters, it's best to just start from some random place and let the computer to improvise. And it also, if it's well trained, it also has this potential, right, to communicate with human, because then I as a human composer, I can just write a piece of music and input, and the computer can naturally, right, know my idea and do some extension, and I can basically communicate. But now it's very difficult to communicate because the system is not well trained. So the problem is just if it's well trained, it will be good.
Why do you think in this case it changes tempo, like drastically changes tempo? So there was no such parameter, or why?
No, it doesn't really suddenly change the tempo because it's not trained, so it doesn't recognize what's happening. It doesn't know how to.
Okay, it just doesn't care what was the input.
Yes, it's just like some non-trained musician, not musically trained people who write some continuation. So yeah, I think the random thing works better here. So the conditioning on melody always it's just expose the problem, right? But whatever, I will also like share this. I will upload everything on the GitHub. So if you have any problem accessing any file, you can just type in this Telegram group chat, and I will check this the files. Okay, and I will add the file. Maybe sometimes I will missing some necessary files. And just remind me if you have difficulty accessing anything, if any materials or files are missing. I can always update. Okay, so I think this is all for my workshop. So any questions?
You don't forget that they probably expect some sort of task, some of them, maybe, I don't know.
Oh, well, so what task do you guys expect? Because, okay, so the thing is that, I'm going back to China like on Wednesday. actually. So I'm available for the next 2 days. So for the task, I mean, we now we have some time to talk. Okay, if you have any ideas, if you have any questions, you can ask me, and we can communicate, and I can follow up in our Telegram chat. But my availability is until the night of Tuesday. Yeah, I mean, after that, I can still follow up, but this will be the internet problem, right? This if I go back to China, I have to use this VPN, and yeah, I cannot access the internet all the time, so might be a little bit difficult to to get in touch. But I think I talked a lot already here. What link? Link to GitHub. No, because I haven't uploaded this yet. I need to upload this to my GitHub, and then I share the link to the GitHub. Yes, I will do this later on. Yeah, this afternoon. Okay. Okay. So let me see. So we have five students here, right? For now. So if you have any thoughts, questions, you can ask me now. I mean, this is the only time I can communicate to you like face to face. After that, we will chat in the group in the Telegram chat. And if you have any question, I can still follow up. But this won't be this convenient, explaining face to face.
Yeah. So in general, the structure as it's outlined on the website is that we have a weekend where we work face to face, and starting from now, you have some days like Monday, Tuesday for asynchronous communication in Telegram in the group. But also, if you want to do some sort of task, as a practice, you can say right now, because you are the group for this workshop, because you are the people who stayed for the first and second day. And we can figure out some sort of task. You can submit it, let's say, like Tuesday in the evening, and Zhengwei can comment on it. You can ask questions like through tomorrow. If you want to practice with something. If you're good and you don't need anything, then it's up to you. So it's a workshop, basically. And any comments, any thoughts, like on the material in general?
Yes.
Was it clear? How clear it was? I saw at least couple people were more or less active commenting. I see maybe well, actually, those who commented, they sort of here. Majority of people who were silent, they disappeared. Yeah.
Yes, hi. I've been silent probably most of the time because the topic is quite new to me, at least this talk about the neural networks like in this extensive form. But everything was good. I understood most of it. And actually, that's why I asked about the GitHub, because I was trying to work with the notebook, Jupyter notebook that you sent, but I'm lacking a file, the training file, to try this out for it to work.
Yes. I mean, yeah, it takes time to figure this out for sure. It's a very intense workshop. I know. And for people who never worked with neural network or Python or Jupyter notebook, it's very difficult, to follow in such a short time. It really takes time. Yes. And this is also why I don't give you homework, right? Because I know people have different levels of background understanding. So I think just follow your pace will be the best way. Yeah, follow your pace. Do what's interesting to you. Do whatever you can. But if you have any question, you can just ask me. Anything.
Which means that the GitHub link will appear later in the group chat.
Yes. Yes.
And also you can follow with some questions. Once you see the link, you download, you try something, and you can follow up with the questions. But this should happen in the next couple of days, yeah, because after that everybody goes and do their stuff. So we're not gonna keep the groups running forever for this school. I mean, for TTSM school, probably there will be some like general group, like we did one last year, but people were not active actually. But the idea is in general maybe to keep it as like some silent community or whatever. So if you have questions later during the year, you can ask, but there is no guarantee that Zhengwei, Torniki, or any of our other tutors will be present in Telegram. But some of your peers, like students who were in workshops, they might answer and so on. But to reach Zhengwei is particularly this couple of days. Yeah.
Yeah, you can always like communicate with me via email, my UCSD email. I can share. I mean, it's also on the website.
Yeah, with academics, it's very simple. You just Google their name, and usually it's the
Sorry.
university page. Yeah, and all emails are open, so it's actually
yeah,
on the
I don't.
website. Yeah.
I mean, I don't use Telegram a lot. I mean, this is only for this thing. I never use Telegram for any other chat. So yeah, the most accessible way, like if you want to contact me later on, like after this workshop ends, the best way is to email me here. Okay, you can write this down, or you just search like UCSD graduate, you know, ABD. Yeah, and then you can see my picture, my introduction, and my email. And yeah, it's always, you can just email me for questions. And I mean, of course, if you successfully trained this neural network, definitely reach out to me. Okay, if you have better results trained, and then it's extremely exciting to see that. Okay, but because I didn't really manage this, and for now, you know, because of life situation, like a lot of other things to do, I have to kind of, you know, stop on this project, no further, you know, continuing with that. Yeah.
Well, if you guys don't have any questions, let's say like the last call for questions we do. I can just comment that I think this workshop was particularly interesting because it's not on a similar in a similar projects you usually not exposed to the internal structure of a neural network. And the brilliance of what Zhengwei is doing is that she actually calculates the neural network almost on paper. So we could see the all the derivatives, all the calculation graph, and if especially if you will follow up, or maybe later will watch again the video, or you would go through the notebook, it's actually becomes obvious that it's just a bunch of formulas which you can write on paper, and that's the whole thing that neural networks everybody's talking about. So if to understand it well, like on a level which like Zhengwei understands it, you actually can calculate it on anything. You don't need like TensorFlow, you don't need PyTorch, you don't need Hugging Face. You can just take a piece of paper and like make a neural network. And that's for me is very the biggest revelation of like our communication with Zhengwei, which happened like before the workshop and so on. And I hope maybe you got this a little bit of feeling of that. This I think was the most precious thing about this workshop. Because as a result, of course, it was like experimental implementation of some sort of like little innovation for the music generation. But we see that result sort of aesthetically questionable. But I can say that majority of this research ends up with something like this, which is aesthetically questionable, and it just contributes to like further research and so on. So that's my ending comments. Like, if you want to say something, please say.
Yes. Yeah, one last thing. Like what I said last year. I mean, I don't know if anyone here is still from last year. Anyone? No, okay. So as I said, so last year I taught, right, this RNN, very simple neural network. And last year I told people, like, next year if we have this again, I will provide something like more interesting, more advanced. And this time I'm seeing this maybe yeah, some similar thing. If we do it again next year, I will also provide something maybe more interesting, more differently. And yeah, just always something new, always something in advance, like every year, and people can see like how this field developed, how I kind of being different, and also yeah, I can see like how people are like doing like everything, whatever. Just that.
But also next year you expect to defend the thesis actually or not?
Yes, exactly. Yeah, I probably will provide a workshop on my dissertation.
Okay, so we will have a Dr. Zhengwei or
Dr. Liu.
Well, okay, guys. If then this also apologies from us, because I think it's a Russian crowd, and we have this culture of being, gloomy and not very asking some unnecessary questions, because we Russians only ask necessary questions. But in general, I think let's give a round of applause, and just you see the right comments, so everybody says that it was nice. So thanks, Jingwei.
Thank you. Thanks everyone for coming. Yeah.
Thank
Thanks
you
for your
very much.
support.
Yeah,
you.
let's keep in touch for this couple days in a group. Expect the GitHub link, and we expect any questions you have up until like Wednesday or something like this. Okay, and see you next week on our second workshop. Okay.
Okay.
Thank you. Bye-bye.
Bye-bye. Thanks, guys. See you. Bye-bye.